Dear students, in this section we are going to discuss one very important concept, that is the application of Gauss law. Suppose we are having 4 point charges, say Q1, Q2, Q3 and Q4. Here you can observe in this diagram the charges Q1, Q2 and Q3 are lying in a closed surface. This is the 3-dimensional closed surface, and this charge Q4 is lying outside this surface. Okay. Suppose we are interested to calculate electric field at any point situated on this closed surface, then what we do? We use Gauss law. And we know the mathematical form of the Gauss law. It is straight: the total flux associated with any closed surface equal to closed surface integral of E dot ds equal to Q enclosed divided by epsilon naught, right? In this equation you can observe this term Q enclosed. Q enclosed is the net charge inside the surface, and this surface is called the Gaussian surface. Okay. This term E vector represents the electric field at any point on the surface. Okay. And one thing very important to note down, that E vector is the total field and may have contribution from charges inside as well as outside the surface. That means in this diagram you can say the net electric field at any point situated on this closed surface will have the contribution of Q1, Q2, Q3 as well as Q4. Okay. Now let us move to few illustrations, and through coming illustration we will learn the application of this Gauss law. So let us move to illustration number 1. In this illustration it is given electric field vector alpha d plus xi cap plus E naught j cap Newton per Coulomb, where alpha, this constant, equal to 1 Newton per Coulomb. Hypothetical closed surface is taken as shown in the figure. You can observe this is the hypothetical closed surface. You can say this is a Gaussian surface. Okay. Find the total charge enclosed within this closed surface. You can observe here this field is having the combination of uniform field as well as non-uniform electric field. X component is non-uniform and Y component is uniform. If this electric field would have been uniform, the net charge enclosed by this closed surface should have been 0. But there is non-uniform electric field also. That means that there will be no total charges enclosed by the closed surface. So let us analyze how to calculate the total charge enclosed by this closed surface. Okay. So let us write the electric field vector. This one. This is the electric field vector. And we know the alpha equal to 1 Newton per Coulomb. Okay. As we discuss, one component, that is the Y component of electric field, is uniform. That means there is no contribution of net flux to this component. Because of this component, there will not be any contribution to the flux to this closed surface. Okay. So we need not to care about this Y component. But electric field, as we discuss, it is non-uniform in the x direction. That means the component of this field will contribute to the net flux. Now let us move to calculate the x component. We need not to calculate for the Y component. We will calculate the contribution of the x component. So let us calculate the flux due to the x component. So let us make the diagram again. Okay. First we will consider the flux passing through this surface. Okay. This surface. Say this surface is surface number 1. Okay. Here you can observe the electric field lines are coming toward the surface. If electric field are coming toward any surface, the flux is called the incoming flux, and that flux should be with the negative sign, right? So also you can observe here at this surface, because this is nothing but YZ plane, and here x equal to 0, that means the electric field, that is the Ex magnitude, should be equal to d. Okay, because x equal to 0 here. And as we discussed, electric field lines of force are towards surface number 1. That means this is the incoming flux and this flux should be negative. And we can observe here the area vector between the angle between the area vector and electric field vector is 180 degree. That means the flux associated with this surface should be equal to Ex multiplied by area multiplied by cos 180 degree, and cos 180 degree equal to -1. That means phi 1 equal to minus Ex multiplied by A multiplied by C. A multiplied by C is the area. Okay, so this is the flux, and phi 1 Ex equal to d. So let us substitute the value of Ex, and now we got the value of phi 1, and phi 1 equal to minus ACD. Let this equation number 1. So we have calculated the flux associated with this surface. Okay. Now let us calculate flux through this inclined surface. Okay. So let us make the diagram. Okay. If electric field would have been uniform, then the flux passing through this rectangle surface, magnitude of the flux passing through this rectangular surface should be same as flux coming through this inclined surface. But electric field is changing with the x direction. That means the magnitude of flux passing through this rectangular surface will not be same in this inclined surface. Okay, so we need to calculate the flux through second surface. Okay, and here we cannot directly calculate the flux by multiplying electric field and area vector. Why? Because electric field having the variation along the x direction. For this purpose, what we need to do? We need to take one elemental strip on the inclined plane here. So let us take one strip on the inclined plane. Let the distance of this strip from this end is L, and the thickness of strip is DL. Okay. The area vector of this strip will be perpendicular to the inclined surface, and electric field is along the x direction. So let us, for the better picture, let us make this situation in the two-dimensional scenario. So let us observe from the z-axis. So we will observe this triangle, and the strip will be like this. Okay, the distance of strip from this end is L, and the thickness of strip is DL, and inside dimension here is C. Okay, the area vector of strip will be perpendicular to the strip like this. This is the area vector, and electric field is along the x direction. That means in the horizontal direction, and we know this angle is theta. That means this angle is theta, and this will be 90 minus theta. Okay, the electric field is having variation along the x direction. So here we can write d phi 2, because we have calculated the flux phi 1. So let us write d phi 2 is the flux passing through this strip. D phi 2 will be equal to Ex multiplied by area of this elemental strip, that is equal to C multiplied by DL multiplied by cos 90 minus theta. So flux through this strip will be this one. Okay, here you can observe this is having the this term is having the variation along the x direction, and here we have the term DL. That means we need to change this DL into dx. So let us write this expression again. Let us do one thing. Let us write dl in term of dx and dy. That means we can make the diagram like this. This is dx and this is dy. And this angle, the inclination of this strip with the horizontal is theta. That means we can write this term dl. Now dl will be equal to dx divided by cos theta. So we got the value of dl, and value of Ex equal to d plus x. So here we can write d plus x in place of Ex, and this term is sin theta. So this is now the final term. Now we can rearrange again, because sin theta divided by cos theta is equal to tan theta. So finally we can write c multiplied by d tan theta dx plus here x multiplied by c multiplied by tan theta multiplied by dx, this one. Let this equation number 3. Now total flux. Total flux is the integration of d phi 2. So we need to make the integration of this. So let us write this integration. Okay. So let us do one thing. Let us write this expression to the next page, this one. This is very simple integral. You can observe the integration of dx equal to x and limit is 0 to b, and here the integration is x square divided by 2. Okay. So this is the final expression after placing the limit, because it's a very simple one. Now we can write phi 2 equal to c dA plus abc divided by 2. Let this equation number 4. Okay. Now we got the value of phi 1. Phi 1 is the flux associated with this surface and phi 2 is the flux associated with this surface. Okay. So total flux through this Gaussian surface, 3-dimensional Gaussian surface, the summation of these two fluxes. This is the incoming flux, this is the outgoing flux. So this is the total flux. Now you can observe this term and this term will get cancelled. So total flux equal to ABC divided by 2. Okay. Now let us apply Gauss theorem. According to Gauss theorem, total flux equal to closed surface integral E dot dA Q enclosed divided by epsilon naught. Okay. Here we will use this term and this term, because we know we need to calculate the EQ enclosed and we have calculated this value. So this value is ABC divided by 2 and we need to calculate this value. So this is the final expression. Now we can write Q enclosed equal to epsilon naught ABC divided by 2. This is the total charge enclosed in this imaginary surface. Okay. Now let us move to next illustration. In this illustration, it is given a system consists of a ball of radius capital R carrying a spherically symmetrical charge and surrounding space is filled with a charge of volume density rho equal to alpha divided by R, where alpha is a constant and R is the distance from the center of the ball. Okay. We are having a system of the charge here. One is fixed charge, that is occupied by the ball, and second charge is having the non-uniform charge density and it is having alpha divided by R relation. Okay. And in next part of the question, it is given find the ball's charge for which the magnitude of the electric field strength vector is independent of R outside the ball. Right. We need to calculate the charge of the ball for which the electric field outside the ball is independent of the distance of the point under consideration from the center of the ball, and it is also asked to find the strength of the electric field. Obviously this electric field will be the constant if it is independent of R, and it is also given the permittivity of the ball and surrounding space is assumed to be equal to unity. Okay. So let us make the diagrammatical situation for this problem. This one, you can observe this is a ball radius capital R, and suppose this ball is having charge capital Q, and suppose we have a certain point here, this point at a distance small r from the center of this ball, and if electric field is independent of R, that means we need to find the electric field at this position. For calculating the electric field, we know we need to use Gauss theorem, and we have the Gauss theorem, that is closed surface integral equal to Q enclosed divided by epsilon naught. Okay. That means for calculating electric field at this position, we need to select a Gaussian surface. For this situation, Gaussian surface should be spherical, a sphere of radius small r. You can observe here the sphere of radius small r will consist of this charge and charge of this medium, and charge of this medium is not uniformly distributed. That's why we need to calculate charge occupied from this surface to this surface for this calculation of this one. For this purpose, what we will do, we will select a Gaussian surface. Suppose we have selected Gaussian surface spherical like this. Okay. And for calculating the total charge enclosed by this Gaussian surface, we need to select a spherical cell. Suppose we have a spherical cell of thickness dr like this. Okay. Now we can apply Gauss law. On this Gaussian surface, electric field will be constant and direction of electric field will be, if charge is positive, direction of electric field will be away from the center. Suppose we have selected certain patch here. This is the electric field vector and area vector is also in this direction. That means this term, left hand term, that should be equal to E multiplied by area of this Gaussian surface, that equal to 4 pi r square. Okay. And now calculate this part. This should be capital Q plus charge occupied by this region. This should be calculated by using the method of integral. For applying method of integration, we need to calculate the charge in this section. We know the surface area of this sphere is 4 pi r square and thickness is dr. That means volume of this region should be equal to 4 pi r square multiplied by dr. Okay. If we multiply this volume with this charge density, we can have the charge dq. dq is the charge occupied by this region. That means the total charge should be capital Q plus integration of dq. So we can write now this expression. Okay. This is the volume of this region and this is the density, volume density. And the limit of integration is started from capital R and to small r. Now let us write this term to the next page, this one. Okay. Now we can observe here epsilon naught is a constant and this 4 pi and alpha is also constant. So now we can write this term, right? Let us do one thing. Let us write 4 pi and alpha outside the integral like this. And integration of r is r square divided by 2. So this integration will reduce to this term and limit is capital R to small r. So after placing the limit, we will have this term. Okay. Now we can write electric field. Electric field should be equal to this term divided by 4 pi r square. Right. Now let us expand this term like this. Now it is required in the question. You can observe this electric field vector is independent of r. If this electric field is independent of r, that means this term, you can observe this term q divided by 4 pi epsilon naught r square and alpha r square divided by 4 pi epsilon naught r square. The summation of these two terms should be 0. Right? It means this term should be equal to this one. Now we can simplify. We will have this value q equal to 2 pi alpha r square. So the charge occupied by this ball should be equal to 2 pi alpha r square. Now the value of electric field should be equal to alpha divided by 2 pi epsilon naught. This is the electric field that will be constant independent of small r.